Hello, my name is Robert Smith and I'm with Academic Assistance, and today we are looking at the concept of resonance. So we're asked to draw the resonance structures of the nitrate ion. So let's get started. Nitrate is NO3 with a -1 charge. So with NO3 minus, nitrogen has 5 valence electrons and oxygen has 6, and there's 3 of those. And then we're going to add 1 electron for the -1 charge. That's going to give us a total of 24 valence electrons. So that's the first thing we're going to want to do in creating the resonance structures, to figure out what our Lewis dot structure is going to look like. And we're going to do that using formal charges. So we needed the total number of valence electrons in order to construct our Lewis dot structure. So we're kind of burying the lead on this a little bit with the idea of there has to be resonance for the nitrate ion. So in general, your skeleton is going to look a little bit like this. And then you would have, if you went ahead and applied that and you looked at the total number of electrons and everything, you would find that this is 24 electrons. You have, for the formal charge, we have nitrogen, which starts with 5, has no free electrons on it, and it has 3 bonds, so it has a +2 charge. That's really, and then we've got oxygen, which starts with 6 valence electrons. Each has 6 free electrons and 1 bond, so that -1. To make this a little more stable, we're just going to take one of these oxygens and give it a double bond instead. So for oxygen prime, we've got 6 minus 4 minus 2. 6 valence electrons minus 4 free electrons minus 2 bonds gives us 0. So that's kind of what the nitrate ion is going to look like. Now, to draw resonance, what we need to ask ourselves is, why did I choose this oxygen up top to have the double bond? Just as valid would be this one or this one. But it's important to recognize that at any given moment in time, that it's not any one single oxygen that has that double bond. Because realistically, when you think about it, why would the molecule choose any given one to have that bond at any given time? So what we have is what's called resonance, which amounts to, in practicality sense, that all 3 bonds have, all 3 bonds that oxygen makes with nitrogen, each oxygen making 1 bond with nitrogen, it acts more like a hybrid between a single and a double bond. So let's draw the resonance. We've got, for 1, we would have, let's look at our first one. Okay. And we've got So whenever you're drawing resonance structures, you're going to use arrows to show the movement of electrons, and only electrons. You don't ever want to use arrows to show the movement of entire atoms. So what's happening here is that you're having this electron, these two electrons coming up here and dropping in, while simultaneously these two electrons drop down to form a new double bond. The result, let's actually move this up just slightly. The result would be oxygen over here is a very similar structure than we already saw, except the double bond is now in the corner. Similarly, you would have an instance where your two electrons would drop in onto the oxygen, and then these two drop down onto make a bond. We get our next form of resonance. And of course, we would have arrows to show that this can come over here and these can go down there. And amidst all this, we would also have double-faced arrows to indicate that this rapidly switches back and forth. Now, again, in practicality, since this occurs so often, so quickly, that the bonds basically form and they look and act more like a hybrid between a single and a double bond. This happens a lot in cases of things like benzene and the like. This is instead of it being that there are several different conformations of the same molecule, that at any given moment in time, any given oxygen could have what appears to be a double bond, and the other two appear to have a single bond. But because of the speed at which this all occurs, every one of the bonds kind of acts like 1 1/3 of a bond. So that's just a brief taste of what resonance is and drawing resonance structures. You'll find that it can get a little hairy sometimes, so it's important to get a lot of practice. And in fact, in all of the upcoming chapters, especially involving chemical bonding, it is very important to get a lot of practice in, much like you did earlier on with some of the more regularly used formulas and such. You just want to, the more practice you get with these, the more familiar you'll become, and the more familiar you become with these, the easier it will be to identify them and create them as needed.